if they're justified.
They're never justified.
Don't bring a bucket. Worst case scenario, you need a bucket, right?
I would never go.
Okay. Let's jump into today's lecture. We're only going to be covering one section today. I think it's section 17. But it's titled Binomial Coefficients. And we'll make sense of why it's called binomial coefficients. But first off, what's a binomial? Right, two nomial coefficients are what come in front, but the binomial just means something that only has two terms, like x plus y. So we expand a binomial by putting it to some power. Now you did this 100 times back when you were in algebra. You did x plus y to some power. So let's go through it really quick. What is x plus y to the 1 equal to?
X plus y.
X plus y. You raise something to the first power. You only have one of them. It's just x plus y, right? What's x plus y squared? Yeah, this is the same thing as x plus y times x plus y, and then you have to distribute to figure out what it is. So the x times the x gives us x squared. We have, so that was this one. We need to do the x to the y gives us a plus xy. We need to do the y to the x gives us a plus yx or xy, doesn't matter what order we write it in. And then plus the y to the y gives us our y squared, right? And if we were to collect like terms, then we'd have, and I'm going to be a bit excessive here. I'm going to write 1x squared plus how many xy's do we have? 2 xy's plus 1 y squared. So these right here are what we call the coefficients for the binomial expansion. These are binomial coefficients. What if we were to do x plus y cubed? What's that now equal to?
X cubed plus.
So this is the same thing. One way we can think about this is x plus y squared times x plus y, right? And we already figured out what the x plus y squared piece was. It's this.
Yeah.
So this is equal to x squared plus 2xy plus y squared all times x plus y. And now we need to multiply the x to each of those things and then the y to each of those things. When I multiply the x to that, what do I get?
X cubed.
We get an x cubed plus 2, if I multiply this by x,
2x squared.
x squared y, we just have one more x, plus when I multiply that by x, what do I get? xy squared, plus, so I multiplied the x into everything, now multiply the y into everything. So multiply the y to that, what do I get?
Y squared.
X squared y plus for this,
2xy cubed.
2xy squared plus finally
Y cubed.
y cubed. Now collect like terms, and once again I'm going to be a bit pedantic with the coefficients. How many x cubes did we have? So we had 1x cubed plus how many x squared y's did we have?
3.
We have 2 right here and 1 right here for a total of 3 that were x squared y. How many were y squared? We have 1 here and 2 there. So 3 xy squared plus 1 y cubed. Now maybe you're noticing a pattern here. When you do it cubed, there's a way to write it so that my exponents in the x count down. 3, 2, 1. Maybe put a 1 there to make it very noticeable. 3, 2, 1, 0 x's. And the y's count up. 0 y's, 1 y, 2 y's, 3 y's. You with me? And now, if we take this and we were to now look at x plus y to the 4th, what would I have to do? I'd have to take this whole thing and once again multiply it by x's and y's. And then collect like terms. And so I would end up with some coefficient, I don't know what number, well in our case it's going to be 1. I'd end up with some number of x4s plus some number of x cubes times y plus some number of x squared y squared plus some number of xy cubed plus some number of y to the 4th, right? And so the whole trick in solving these problems, multiplying these out, is trying to figure out what these coefficients are going to be. And so what we're going to be doing today is coming up with ways of talking about these coefficients and making a connection between these coefficients and unexpectedly counting subsets of a certain size. Somehow these coefficients and counting subsets are one and the same thing, and they're very related to each other. And that's the connection we're going to be focusing on today. Now going back to in your algebra days, expanding this all out, this is becoming a nightmare. Right? And so if I were to ask you to do something like what's x plus y to the 5, that would take, I mean, it's not too much time, but still, it takes a good amount of time multiplying all those out and collecting all your like terms. Nobody wants to do that. And so you were introduced to, in grade school, something called Pascal's triangle. Pascal's triangle, how does it work? You start with a 1, and imagine infinitely many zeros to the left and infinitely many zeros to the right. I just don't want to write all the zeros. You with me so far? And then a 1. The rule is, on the next row, between each of the two numbers on the previous row, so there's really a 0 right there, a 0 right there, and zeros going on forever, add those two numbers together and put the number there. Add those numbers together, put the number there. With me? And once again, imagine zeros going all the way. Add those two numbers together, put it there. Add those two together, put it there. Add those two together, put it there. Once again, add those, add those, add those, add those. You see the pattern? All right, let's alternate. You're each going to tell me which number to write, starting with you, 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 you. What comes first? For the next row here, add these two numbers together. What do I write?
1.
1. Next is?
7.
Next is?
21.
21. Next is?
I'm sorry, I can't.
Oh, that's a 15 and a 20.
Oh, it's 26. Wait, 35?
35. 15 and 20, 35.
Oh, okay, sorry.
You can move up if you want. 35, once again, 20 and 15 then gives us 35. 15 and 6 gives us 21, 7, 1. See the pattern? And notice symmetry down the middle. Okay, so what's the point of this triangle and how does it help you? Well, we associate with the first row. This is the same thing as looking at the coefficients for x plus y to the 0. What's anything to the 0?
1.
Huh? 1. Anything to 0 is 1, because why is it 1? What's a negative exponent? Negative exponent means put it downstairs, right? So let's look at a to the 1 times a to the negative 1. You know that when you multiply terms, you add exponents. So one way to think about that is a to the 0. Another way to think about that is put that downstairs. So you get a to the 1 over a to the 1. What's a number divided by itself? 1. So a to the 0 is just 1. Anyways, so x plus y to the 0 then is just going to be anything to the 0 is just 1. So this would just evaluate to 1. So that's what its whole coefficient would be. There'd only be one coefficient, namely 1. What's x plus y to the 1 equal to?
Just x plus 1.
Just x plus y. That's it. So we wrote that right here. That's 1x plus 1y. What was our coefficient of x? 1. What was our coefficient of y? 1. Now, x plus y squared, what do we get? So we wrote this one out. What was it? 1, 2, 1 were our coefficients. 1, 2, 1. Similarly, x plus y cubed. What were its coefficients? We did that one. 1, 3, 3, 1. And if we would have multiplied out x plus y to the 4 now, x plus y to the 4, and we would have collected like terms, we would have found out that it was 1x to the 4 plus 4x cubed y, 6, 4, 1, if we would have taken the time to multiply all that out. And now, when someone asks me, what's x plus y to the 5, I can calculate it real quickly without even having to do all the expansion. I just look at this triangle, and I instantly say it's going to be 1 times my biggest x term, so that's x to the 5, y to the 0, plus 5, decrement my x1, so this was x to 5, so now it's going to be x to the 4, y to the 1, plus, my next number was 10, x cubed, y squared, plus my next number was 10, x squared y cubed, plus my next number was 5, x y to the 4, plus 1 y to the 5. And that's what it would multiply out to. And so that's much, much quicker than having to expand all that. You with me? And so now, if I were to ask you something on your test, like calculate x plus y to the 6, that's something that you could easily do just scratching up this triangle. It's just right there. And these would be your coefficients, and you'd expand it out the exact same way, right? But even now, this can get a bit tedious if I were to ask you to do something like x plus y to 17. I don't want to have to construct 18 rows of this thing just to figure out what that's going to be. That would take forever. And even this will start blowing up. Especially if I said, I just want to know the term here that had x to the 10, y to the 7. I just want to know that one's coefficient. When you expand this out, how many of these terms do you get? A question like that. And that would be a ton of work for what we're going to find out is actually a pretty easy thing to come up with. So that's what we're connecting today. The section's all about binomial coefficients. It's these numbers right here. Somehow this is connected to counting subsets. And so that is the next connection that we're going to be making. And then we're going to tie it back to this and see how this and counting subsets are somehow related. Good so far? Okay. And just out of curiosity, is this the first time you guys were seeing Pascal's triangle? Do you remember it from the past? Good. Okay. So now we're going to introduce a new notation. Let n and k be some natural numbers. 0, 1, 2, 3 doesn't make sense with negative numbers, so they're not negative. They're naturals. Good so far? Okay, so then we have this new notation. Write it big once. You do an n over a k, and then you put it in parentheses. And we read that as n choose k. N choose k, as in you're making a choice. N choose k is how you read that. So let n and k be natural numbers. Then n choose k denotes the number of k element subsets that can be made from an n element set. If I have n options, how many ways can I choose k of them? Let me give you an example. Say I had 10 people in this room, and I was going to choose 3 of you to win a trip, win some award. How many ways could I choose 3 people out of a group of 10 people? With me? So that's what this notation is going to talk about. So n choose k, it's how many ways we can choose k things from n options. It's how many k element subsets you can make from an n element set. Because choosing 3 out of 10 people is the same thing as making a 3 element subset of those 10 people that you started with in your initial set. Okay. So let's go over some examples. We're going to take the case where n is 5. Or in other words, we're talking about a 5 element set. Now it doesn't matter if they're the numbers 1, 2, 3, 4, 5, or if we pick the letters A, B, C, D, E, F, whatever. E, not F. Okay. So now, let's go and just write out this notation answering some questions. So 5 choose 0. This is asking how many 0 element subsets can I create from this 5 element set? How many 0 element subsets can I create? How many sets have 0 elements in it? What's a set with no elements in it? The empty set. So there's only one subset I can create of this set that has no elements in it. It's right here. That's the only one. So, maybe we'll scribble it up here. So 5 choose 0 is 1. Or in other words, if I've got 5 people and I'm going to choose 0 of them to get an award, how many ways can I do that? 1 way. I choose none of it. That's the only choice. Okay, now let's look at 5 choose 1. How many 1 element subsets can I create from this list? 5. Perfect. And what are the 5? I can have the set just containing 1. I can have the set just containing 2. I can have the set just containing 3. I can have the set just containing 4. And I can have the set just containing 5. Right? Okay, a little bit more tricky. How many 2 element subsets can I create?
20.
20? Well, we don't really have a good way to count that right now, so let's just brute force it. How many 2-element subsets can I create? I can pick 1 and 2, right? I can pick 1 and 3. I can pick 1 and 4. I can pick 1 and 5. I can pick 2 and 3. I can pick 2 and 4. I can pick 2 and 5. I can pick 3 and 4. I can pick 3 and 5. And then finally I can pick, 4 and 5. So how many was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I miss any? If I've got 5 people here and I may choose 2 of them to go on a trip, those are the only options. I could have picked those 2, 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 or those 2. It's every possible combination. All 10 of them. So this came out to 10, and we had to figure that out just by counting. How many ways can I choose all 5 elements? 5 choose 5. How many 5-element subsets can I make of that list?
25.
If I have 5 people in the class,
1.
and I may choose 5 of you to go on a trip, how many ways can I choose you?
1. You choose all.
1. I can choose all of you. That's the only choice. If there's 5 options and I have to choose 5, I have to choose everyone. There's only one way to do that. How many ways can I choose 4 of you?
5.
Choosing 4 of you to go on a trip is the same as choosing 1 of you to stay behind. Right? If there's 5 people in the class, choosing 4 of you to go on the trip is the exact same thing as choosing 1 person to stay behind. So I can do the set containing everything except 1. I can do the set containing everything except 2. I can do everyone except 3, everyone except 4, and everyone except 5. Those would be my only 5 options. So this would still be 5. And you see how this is kind of the counterpart to that, the same way this is the counterpart to that. Choosing 5 people to go on the trip is the same thing as choosing 0 people to stay behind. Choosing 4 people to go on the trip is the same thing as choosing 1 person to stay behind. And then choosing 2 people to go on the trip is the same thing as choosing 3 people to stay behind. So what's 5 choose 3? 10. And so you see that symmetry to it. 1, 5, 10, 10, 5, 1. And surprise, surprise, it looks the exact same as this. Or in other words, those numbers came out exactly the same way as the coefficients on this. 1, 5, 10, 10, 5, 1. And for some reason, these things are connected. And I'm going to try and make that intuition appeal to you by the end of the lecture. But it turns out they're very closely related. And so our initial question here, when I said, what's the coefficient? If we were to expand this out, it's kind of like asking, how many ways, if there's 17 people in the class, could I choose 10 of you to stay and 7 of you to go on a trip? And it turns out whatever that answer is the same thing as a coefficient to this term if I were to expand this all the way out. Those 2 questions are the same. Okay. So introduce the choose notation. We don't yet have a formula for it. Don't worry, we'll get a formula for how you do that so you don't have to sit there and think how to count. But let's first come up with some special cases. So we did the special case where n is 5. Now let's think about it for n being any number. So let's go through the thought process, but this time we're looking at a class that has n students in it. And it could be 10, it could be 100, it could be 1,000, whatever it is, it's just some number. With me? Okay, so I've got n people in my class now. How many ways can I choose 0 of you to go on a trip?
1.
Once again, 1, yeah, just the empty set, choosing no one. All right, n people in the class, how many ways can I choose 1 of them? N ways, perfect. And now, let's jump over here for a second. N people in the class, how many ways can I choose all of them? 1. If there's n people in my class, I got to choose n of you to go on a trip. There's only one way to do it. Take you all. N choose n minus 1. So this is something like 10 choose 9, or 100 choose 99. Some number choose 1 less. This is the same as choosing 1 to leave out. So how many ways can I leave 1 out? n ways. Perfect. So same exact symmetry then. Now let's try a harder problem. And think about n choose 2. And we want to come up with a formula for this. I've got n options. How many ways can I choose 2 of them? And we're going to see if we can come up with a formula for that. Now let's pick a concrete case that we can actually write them out. 5 is a good number. Maybe we'll do 6 as an example. So let's pick n to be 6 to help us get the idea, and then we'll go from there. So let's say that we've got 6 people. 1, 2, 3, 4, 5, 6. And I want to choose 2 of you to go on a trip. So we're looking at 6 choose 2. And we're trying to come up with some sort of formula, some sort of pattern we can find with this. You with me? So I'm counting how many 2-element subsets I can make from a 6-element set. Okay? So I'm going to be writing out 2-element subsets, and I'm going to write rows of them with some pattern. Now first off, how many 2-element subsets can I create where 6 is the smallest element in my subset? So I have 6 and something else, but 6 is the smallest thing in there. None. I can't pick another number and have 6 be the smallest thing in there. You with me? Okay. But what about, so maybe make a table here, with 6 as the smallest. There wasn't any. Okay, what about with 5 as my smallest element?
1.
How many subsets can I make with 5 as my smallest element?
1.
5, 6. That's the only one, right? And so we got 1 of them. What about with 4 as my smallest element?
2.
I can have 4, 5, and I can have 4, 6. What about with 3 as my smallest element?
3.
I can have 3, 4. I can have 3, 5. And I can have 3, 6. Okay, what about with 2 as my smallest element? 4. I can have 2, 3. I can have 2, 4. I can have 2, 5. And I can have 2, 6. And finally now with 1 as my smallest element.
5.
I can have 5 of them. I can have 1, 2. I can have 1, 3. I can have 1, 4. I can have 1, 5. Sugar. 1, 5. And finally I can have 1, 6. And so, how many total do I now have? Just tell me what you're thinking in your head. You don't have to calculate it.
1 plus 2 plus 3 plus 4
It's
plus 5.
1 plus 2 plus 3 plus 4 plus 5. And so whatever 6 choose 2 is, this is equal to 6 choose 2. 1 plus 2 plus 3 plus 4 plus 5. So notice we added up all the numbers and we ended right before whatever this number was. So if I were to ask you to look at something like, not 6 now, something like 8 choose 2, what would that be? We do the exact same thing. We have 0 where 8 was a minimum element, 1 where 7 was a minimum element, 2 where 6 was, 3 where 5 was, 4 where 4 was, 5 where 3 was, 6 where 2 was, and 7 where 1 was. And so 8 choose 2 would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Repeating the same pattern. So this was when we had 6 elements, right? Now imagine instead of 6 now, we instead had 8. If I redid the process, then the 8 here, there would have been none with 8 as a minimum element. With the 7 here, there would have been 1. It would have been 7, 8. And there would have been 2 with 6. There would have been 3 with 5, etc. And so that's where we're getting the 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. And so it's going to end one smaller than whatever that number was. Make sense? And so that's what we're going to quickly prove in general now, is that n choose 2 is always equal to 1 plus 2 plus 3 dot 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 up to one number smaller than whatever that n was. If that n was 5, then the last number we add here is 4. If that number was 8, then the last number we add here is 7. Good? Okay, so let's go over. Let A be some unelement set, where n is, I don't know what I said, some n element set, where n is just some natural number, whatever it is. Good so far? Then, by definition, n sub 2 counts all the 2 element subsets. That's what we define this notation to be. N choose k is all the k element subsets you can make from an n element set. So I already know n sub 2 counts all the 2 element subsets. Now I'm going to show that this also counts all those 2 element subsets by doing exactly what we did over here, just listing them out. 1, 2, 3, 4, 5, etc. So observe that there are 0 2 element subsets with n as the minimum element. And then there's going to be 1 with n minus 1 as the minimum, namely n minus 1n. 2 with n minus 2 as the min element, namely n minus 2 and n minus 1, n minus 2 and n. 3 with n minus 3 as a min element, counting all the way up, dot, dot, dot. And n minus 1 with n minus 1, which is equal to 1 as the minimum element, just following the exact same pattern. So minus 1, minus 2, minus 3, minus n minus 1, which n minus 1 is just 1. Distribute the negative gives you a 1. So then, counting all of them up, we get 1 plus 2 plus 3 all the way up to n minus 1, counts all the 2 element subsets. Therefore, they both count the same thing, therefore they're both equal. Okay, but that doesn't really help us figure it out too well. If I gave you something like 100 choose 2, who wants to do that? 1 plus 2 plus 3 plus 4 plus 5, da da da, all the way up to 99? What a nightmare. I don't want to do that. Sounds familiar. We already played with a problem like this early in the year. Help prime your brain for it. So let's go over it once again. So now I'm going to show you that this formula works, and you can just use this formula. Let's go over the proof of that. What does n choose 2 equal? It equals 1 plus 2 plus 3 plus dot 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 all the way up to n minus 1. That's what we showed up here. N choose 2 is just equal to that. So n choose 2 by itself is just 1 plus 2 plus 3 dot 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 all the way up to n minus 1. Good? Now if I multiply it by 2, that just means add up those numbers twice. The second time I add those numbers, I'm just going to add them up in reverse order. So since I have 2 of them, I also get another 1 plus 2 plus 3 plus 4 plus dot 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 all the way up to n minus 1. Now I'm just going to add all those numbers up, doesn't matter what order you add them in. What's 1 plus n minus 1? If you have 1 plus n minus 1, well that's equal to, you still have your n, what's 1 and negative 1? 0. So these two add together to just give us n. What's 2 plus n minus 2? N. What's 3 plus n minus 3? N. If I keep doing this, plus n plus n. So we keep getting n every single time if we do this tricky way of adding it up. Right? So 2 times n minus 2 is equal to n plus n plus n plus n plus n. How many times do we have this n?
n minus 1 times.
N minus 1 times, because that's how many terms we have listed out here. 1 to n minus 1. If n was 8, then this is listing up 7 terms. 1 plus 2 plus 3 all the way up to 7. Good? Okay. So, I get that, scribble over here, 2 times n choose 2 is equal to, n, how many times did we have n? We had it n minus 1 times. N plus n plus n plus n plus n, n minus 1 times is the same thing as n minus 1 times. Right? If you have 5 plus 5 plus 5 20 times, that's the same thing as 5 times 20. 100. So I have n plus n, n minus 1 times. That's n minus 1 times, or n minus 1 times n.
You just divide by 2.
Divide both sides by 2, and now I get n choose 2 is equal to n times n minus 1 all over 2. And so that quickly adds them up. And so now let's look at our example. 100 choose 2 is the same thing as 1 plus 2 plus 3 plus 4 plus 5 dot 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 all the way up to 99. So what should that be? Adding all the numbers from 1 to 99. Or sorry. Adding all the numbers, yeah, from 1 to 99 is going to be You're just plugging in 100 into this. So let's plug it in the case of that. So 100, choose 2. What's this equal to? You're replacing your n with 100. 100 times, what's 100 minus 1? 99. All over 2, which is equal to?
4950.
Yeah, it would be easier to double it than cut it in half, maybe? I don't know. What's 99 times 100?
9900.
That's just 9900 over 2. Now we're doing half that. What's half of 99?
49.
49.5. So 4950. And there we go. That's what it is. But you could always just plug that into your calculator if you can't do the arithmetic in your head quick. And so you can figure this out for any number now. Maybe we should have done 101, and it comes out a little nicer. That would have been 101, this would have been 100. So if we do 101, choose 2, that's adding up all the numbers from 1 to 100, which I already had you guys do that as an exercise. So let's do 101, choose 2. That's going to equal to n, which is 101, times 100, all over 2, which is equal to 100 divided by 2 is 50. And then multiply the 50 by that gives us 5050. Now, how did you guys before add up all the numbers from 1 to 100? How did we do it? When you were adding up all the numbers from 1 to 100, what was the trick? So you had 1 plus 2 plus 3 plus ... plus 97 plus 98 plus, shoot, didn't give myself enough room, plus 99 plus 100.
Was to do the same thing in the
But, so then we have this 100 to the side. What you did is you combined the 1 with the 99. What's 1 and 99? 100. The 2 and the 98? 100. The 3 and the 97? And you could think about we're combining the 0 with the 100, gives you a 100. So you're going to get 100 50 times, so you have 50 100s. With 50 in the middle, could it be paired to anything? So 50 100s plus 50. What's 50 times 100? 5,000 plus 50. 5,050. So it's the exact same thing, and it's using a similar pattern to what we did here. Make sense? Okay. So there we go. We now have this way of doing this and choose 2. Now, we want to come up with all the coefficients in general and look at how much work we've done for just a couple special cases. So I now know how to do n choose 0. I now know how to do n choose 1. I now know how to do n choose 2. I know how to do n choose n minus 1, n choose n. What about something like n choose 5, and n choose 6, and n choose 7? We're not getting anywhere. Right? Feels like we're just handling a bunch of special cases. Well, let's notice another thing. I already pointed out, shoot, just move the camera, but Pascal's triangle here is symmetric, which means the coefficient over here should be the same as the coefficient over here. What's that hinting at is that n choose k should be the same as n choose n minus k. What do I mean by that? Give me an n and give me a k. Give me an n.
7.
7. Choose, give me a k.
500.
5. You want it to be smaller, otherwise the answer is always going to be just 1. Or 0, I mean. How many ways can you choose 100 elements from a 7-element set? You can't, so it's 0. Okay, but 7 choose 5. So what this is saying is whatever 7 choose 5 is should be the same thing as 7 choose 7 minus 5. What's 7 minus 5? 2. So we're saying that these two things should be equal. Now how can we intuitively make sense that these two things should be equal? This says if I have 7 people, how many ways can I choose 5 of them to go on a trip? Right? Notice that if I have 7 people, choosing 5 to go on the trip is the same thing as choosing 2 to stay behind. So that's why they're always equal. Anytime I choose k, I choose to leave behind n minus k. Make sense? And so, that's what gives me this symmetry right here. Or that's how this choose notation preserves that symmetry. So now let's go through it, but it's going to be that exact argument. Where my a's are going to be, every time you choose k, you leave behind n minus k in some other set b. And so while A is counting all your 5-element sets, B is going to be counting all your 2-element subsets. So let's run through it. Let n and k be any two natural numbers, and let A be some n-element set. Now we're looking at n choose k. All the ways that we can choose k elements from an n-element set. That could be like 5 choose 7, or 7 choose 5, I mean.
Hi, Miss Haley.
We're missing Caleb, and we're missing Olivia.
Nice to have your class back.
Yep. All right, so n choose k is all my k element subsets from an n element set. That's what it is. And there has to be some number, I may call that number n. What do I need to prove? I need to prove that n choose n minus k is that same m. If it's that same m, then those two have to be equal to each other. Right? In other words, if there's 7 of you and I'm choosing 5 of you to go on a trip, and there's m ways I can do that, then if I were to count all the 2-element subsets, or all the ways I could leave 2 of you behind, that better also be m, in order for those to be equal. You with me? Okay, so let m be whatever n choose k is equal to, and let a1, a2, am be all the k element subsets of A. Now, for each k element subset of A, for each a1, I'm going to let b be its complement. So I got that line above it, that's the complement of a1. What's the complement of the set? Remember that? So let's go back to a concrete case. We'll say that here's my set A. So it has 8 elements. You with me? So pick some subset of A. So let's say that A1 was equal to the subset 1, 5, 6, 7. Then B1, if B1 is equal to A1's complement, it's equal to the set of everything not in A1. So A1 had 1, so we don't have 1. A1's missing 2, so we have 2. A1's missing 3, so we have 3. A1's missing 4, so we have 4. A1 has 5, so we don't. A1 has 6, so we don't. A1 has 7, so we don't. A1 does not have 8, so we do. So the complement is everything not in the set. With me so far? Mm-hmm. So every time I pick A1, I leave behind B1. B1's everything that wasn't in A1. So I'll let B1 be A1's complement, B2 be A2's complement, Bm be Am's complement. Now observe that every n minus k element subset is a complement of some k element set. Anytime you make an n minus k subset, you left behind k elements. Anytime I choose 2, I left behind 5. When we were doing, let's see, in this example it's 8. So if I were to pick a 5-element subset, I would have to leave behind 3 elements. So anytime you do n minus k element subset, you are leaving behind k elements. So observe that every n minus k element subset is a complement of some k element subset. And that there are m of them. Therefore, there's m of those, there's m of those, so they have the same count. So they're equal to each other. So you get that symmetry that your intuition told you should be there. Good? Okay. Now the big part, tying this together with this binomial expansion. What does this have to do with binomial expansion? How are these things related to coefficients? Let's now try and make that connection. Okay. Here's how I'm going to think about this. Starting out in our simplest case, we're looking at x plus y to the 1. We know that that's x plus y. With me? I need to say that this is somehow counting all the subsets I can make of a 1-element set. Now let's pick some 1-element set. In our case, we'll just pick it to be the set containing 1. What are all the subsets I can make of that? I can have this as a subset. And what else can I have? The empty set. So these are the two subsets of that. The way I'm going to think about this is x means don't include the element, y means yes, include the element. So x plus y to the 1 is the same thing as x plus y. I can think about the x as not including it and the y as yes, including it. And so I can think about this as counting those two subsets. With me so far? Let's try another one. X plus y to the 2 now. So I'm looking at some 2-element set. Right? What are all the subsets I can choose? I can choose a subset where I don't include any elements. Right? Should I include the first one? No. Should I include the second one? No. So in other words, that gives me the empty set. Let's look at the next one. Should I include the first element? We'll say yes. And should I include the second one? No. That gives me the set containing 1. Next one. Should I include the first element? No. Should I include the second element? Yes. That gives me 2. Next one. Should I include the first element? Yes. Should I include the second element? Yes. That gives me 1, 2. And so when you take x plus y and you square it, you get an x times an x. That's right there. You get an x times a y. That's right there. You get a y times an x. That's right there. And you get a y times a y. That's right there. And so x, don't include the first, don't include the second. That's exactly what we meant by the empty set. Include the first, not the second. That was 1. Include the second, not the first. That was 2. And then include them both. That was 1, 2. So I can think about that as counting all those subsets. For our next one, let's look at that. If I have x plus y to the 3, I'm saying that expansion should somehow be counting all my 3-element subsets of a 3-element, or all my subsets of a 3-element set. So what's my 3-element set? We'll just do 1, 2, 3 for now. You with me? And what are all the options? I can start out with the set. Don't include the first. Don't include the second. Don't include the third. X, X, X. And we would think about that as mapping to, which set does that represent? The empty set. So we're on here. That one represents the empty set. What about the set that's y, x, x? The set contains just the first element, or in this case, 1. X, y, x? Just 2. X, x, y? Just 3. Y, y, x? 1 and 2. Y, x, y? 1 and 3. X, y, y? 2 and 3. Y, y, y? 1, 2, 3. Right? So now when I just brute force multiplying out a binomial this way, not collecting any of my terms, notice how every term goes exactly to one subset of the 3-element set. Now what happens when I combine like terms? How many did I have with 3 x's? 1. How many did I have with 2 x's and 1 y? 2 x's and 1 y? 3. How many with 1 x and 2 y's? 3. And how many with all 3 y's? 1. You're right. So think about what the x meant. The x meant don't include the element. If I had x all 3 times, that meant don't include any of them. So that's the same as how many 0-element subsets were there of a 3-element set? 1. It's one that didn't include any of them. This one had 1 y, which meant we only included 1 element. So how many subsets had 1 element in them? 3. How many had 2 elements in them?
3.
How many had all 3 elements in them?
1.
And so you see how these coefficients are now counting the number of subsets you can make from an n-element set. You seeing it? And so that's the connection with how adding these things up is giving you the same thing as counting subsets. And so this is the exact same thing as if I would have written it out. 3 choose 3 times x cubed plus 3 choose 2 times, 3 choose 0, 3 choose 1, x squared y, plus 3 choose 2, xy squared, plus 3 choose 3, y cubed. Gives me the exact same thing as this. How many ways can I choose 0 elements? 1. How many ways can I choose 3 elements from a 3-element set? 3. How many ways can I choose 2? 3. How many ways can I choose all 3? 1. So it gives me those exact same coefficients. And so, forget trying to now manually expand these things out and then adding up all the like terms. What is it for something like x plus y to the 8? What is my first term going to be there using our choose notation? If we did x all 8 times and y 0 times, then that meant we chose 0 of them. X meant don't take it, y meant take it. And so that's just going to be 8 choose 0. Whatever that is. And what's this one going to be? If we didn't take 7 times and we took 1 time, that's just going to be 8 choose 1. This is just going to be 8 choose 2. This is just going to be 8 choose 3. This is just going to be 8 choose 4. This is just going to be 8 choose 5. Because again, we said yes to 5, no to 3. This one is when we said no twice, yes 6 times. So that's 8 choose 6, 8 choose 7, and finally 8 choose 8. You with me? So now if I just gave you a formula that works for any time we do choose. Notice that you know how to do very special cases. You know 8 choose 8 is 1. How many ways can I choose all 8 elements? 1. How many ways can I choose 7 or leave 1 behind? 8. And you know how to do 8 choose 0. You know how to do 8 choose 1. You now know how to do 8 choose 2. What's 8 choose 2? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Or 7 times 8 divided by 2. 7 times 4, 28. And so you know that this one has to match that, but there's still these middle terms that we just don't have a good way of doing yet. But if I can help you in general calculate this choose notation, then now any expansion you can pretty much just figure out. And it's not a big deal. Right? If I gave you an easy way to calculate each of those. I know you only know how to do some so far. So now in general, here's the binomial expansion. I want to show it to you in all its glory how it will be written out. So in general, x plus y to the n. If we were to multiply this out, I can always write it as n choose 0 times x to the n, y to the 0. Here's a concrete case of 8. Plus n choose 1. Notice that our x's keep decrementing, getting smaller and smaller, and our y's keep incrementing. So x gets 1 smaller, y gets 1 bigger. So on this, x went from 8 to 7, so we go from n to n minus 1. The y went from 0 to 1. Same thing, plus n choose 2, x to the n minus 2, y to the 2. Notice that the y is always the same as however many we're choosing. Because that's what we meant y to symbolize is, yes, I choose that element. X meant don't choose the element. Go ahead. Going all the way to the end, n choose n, if we chose all n elements, then y had to be all n. And x had to be 0 because we didn't leave any behind. So our x is constantly decrementing and our y is constantly incrementing. So there it is written out. Now here's the formula that you're going to see, and I know that this is dense notation for you guys, but there it is in all its glory now. What's x plus y to the n? It is equal to the sum from k equals 0 to n. You remember the sigma notation? Oh, you were gone for it. You need to watch the lectures.
Thank you.
Very welcome. Of n choose k times x to the n minus k, y to the k. So you plug in k equal to 0 and write out that term. So replace all my k's with zeros, and that's my first term. N choose 0, x to the n minus 0 is n, y to the 0 is 0. Now add it to what you get when you plug 1 in. So now plug 1 in. N choose 1, x to the n minus 1, y to the 1. Now plug 2 in. Now plug 3 in. Keep plugging in until you get to whatever that n is. So your last term is what you get when you replace all your k's with n's. So you end up with n choose, replace the k with an n, times x to the n minus n is 0, times y to the n. See that? So that's the formula that your book has written there, and hopefully that formula makes sense now. Okay. So that's the big connection. Once you see how these binomial coefficients connect to counting k element subsets of an n element set, then you see the connection between this choose notation and binomial coefficients. The last thing I need to connect for you now is why Pascal's triangle works, and then we're done. With me? So what's 0 choose 0? How many 0 element sets can I make from a, how many 0 element subsets can I make from a 0 element set? So here's my 0 element set, the empty set. How many subsets does that have? One. Just the empty set. So how can I have a 0 element set and choose 0 of them? One way. Right? A 1 element set, how many ways can I choose 0 of them?
One.
A 1 element set, how many ways can I choose 1 of them?
One.
One. Once again, next row. If I have a 2 element set, how many ways can I choose 0? 1. If I have a 2 element set, how many ways can I choose 1 of them? 2. I can pick the first or I can pick the second. And 2 element set, how many ways can I choose 2 of them? 1. And so, once again, if you keep thinking it through, you'll see that these are given the exact same numbers so far. Now, why does this work? This works because of Pascal's identity here. It says n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. Let's pick a concrete example to see that in action. I'm going to pick my n to be, we'll say that we're trying to calculate this one right here. So what would be right here if I were to keep writing this out? That one would be 6 choose 3. I want to say, if Pascal's triangle works, in the case over here it's 20, if Pascal's triangle works, 6 choose 3 better be the sum of those two things. Because how did we get that 20 there? We added those two things together. So what I'm trying to say is that 6 choose 3 is equal to what?
5 choose 2 plus
5 choose 2 plus 5 choose 3. Now that's what this is saying in general. N choose k, in our case we have a 6 and 3, is equal to 1 smaller than n, since it comes from the previous row, 1 smaller than n, choosing 1 less than our k, plus 1 smaller than n, choosing the same as our k. And we need to show that this is always and forever the case. With me so far? Okay, so let's look at 6 choose 3. So I have 6 people in this class, and I need to choose 3 of you to go on a trip. With me? Now, I can start out by saying, Alex is a lock-in. We're for sure taking Alex, no question about it. So now, how many spots are left? 2. And how many people do I have to choose from? 5. So it's now 5 choose 2 if Alex is a lock-in. So here's a number of ways that we're for sure taking Alex. Now what if I were to say, there's 6 of you, we're going to choose 3 of you, but Alex, no, you're disqualified. Bad behavior. So we're for sure not going to include Alex. So how many people are there to choose from? 5. And how many options are available? 3. So 6 choose 3. I can count all the ways that don't include Alex, all the ways that for sure include Alex, plus all the ways that for sure don't include Alex. And that counts all the way I can pick all 3 of you. Make sense? So it's that same argument. I'm not going to write it out because I'm afraid you'll just get lost more in the notation than in the idea of the proof. But that's the idea of the proof. How many ways can you do n choose k? Pick some special element, call it Bob. Here's all the ones that for sure include Bob. Here's all the ones that for sure don't include Bob. And you either do or do not include Bob. Count all the possibilities, and there it is. So with this notation always works. And so Pascal's triangle always works for giving us these coefficients. And so there's our proof for Pascal's triangle. Okay. Before we jump into examples, maybe let's do break, and then we'll come back and do examples. All right, let's continue and finish up our lecture. So before I go to this next part, I want to remind you of a counting technique you used from your last section. So you remember last week we counted how many words we could make using the letters from Mississippi. So we ended last lecture with an example just like this. And remember, we want them to be unique words. So the stupid answer right out the door was, let's see, how many letters were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the dumb answer was 11 factorial because swapping these two letters still gave me the exact same word. And so what we had to do is we had to divide it up into equivalence classes, which is how many give me the exact same word. How many ways could I have, using these letters, written out Mississippi just like that? And so, remember how to do that? Did a bunch of examples on your problem. We said, let's call this I, the first I, this I, the second I, this I, the third I, this I, the fourth I. We call that S1, S2, S3, S4, P1, P2. And so if I'm going to exactly spell out Mississippi, sorry, do I have it up there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11-ish. How many options do I have for what letter goes first? 1. How many options do I have for what letter comes here? I have 4 I's I can choose from. If you think about this as like Scrabble tiles, how many options do I have for this Scrabble tile? 4. How many options for that S? If I had the Scrabble tiles, imagine those are actual Scrabble tiles. How many choices do I have for what to put as my S there? So I got my M, I got my I now. How many options do I have for that S? 4, because I have 4 S Scrabble tiles. How many options now do I have for my second S? 3. How many options do I have for my second I? 3. How many options for my third S? 2. That's my S, 2. How many options for my last S? 1. How many options for my third I? 2. How many options for my first P? 2, since there's 2 P's. For my second P, 1. And then finally for my last I, 1. So for this particular word, there was 1 times 4 times 4 times 3 times 3 times 2 times 1 times 2 times 2 times 1 times 1 choices on how we could do that. Or in other words, if you count it out, it's 4 factorial times 4 factorial times 2 factorial. Where did the first 4 factorial come from? The fact that we had 4 I's. Where did the second 4 factorial come from? The fact that we had 4 S's. Where did the 2 factorial come from? Our 2 P's. Now you could also say times 1 factorial for our M, but what's 1 factorial? 1, so multiplying by 1 doesn't change anything. So 11 factorial, this is counting all the ways that we could arrange those letters into words. But now, a bunch of those arrangements are going to give us the exact same word. In the example where we're actually looking at the word Mississippi, there was 4 factorial times 4 factorial times 2 factorial ways that we could use those Scrabble tiles to get Mississippi. Remember that? Okay, so remind you of that counting. Now, let's go on now and answer the question that this choose notation is supposed to give us. How many ways are there to make a 4-element subset of a 10-element set? Let's say that here is our set. Good? I need to make a 4-element subset. How many ways can I do that? Well, first I need to choose which one goes here. How many ways can I choose the first element in my set? 10. I have 10 choices for how to choose this. And let's just go through some hypothetical scenario. Which one should we say I chose? 4. And let's say that that choice happened to be 4. But it could have been 1, 2, 3, whatever. Okay, so how many choices do I have for what comes next in my set? 9. And let's make a hypothetical choice. 6. How many options for what's left? 8. Make a hypothetical choice. And then last, 7 and 7. Okay. So there we go. There were 10 times 9 times 8 times 7 ways that we could do this. You with me? Now what is our problem with calculating it that way? is this one, we happen to have the set 4, 6, 10, 7. But notice that that would have been the exact same thing as the set 6, 4, 10, 7. So this was tracking with order. So this is the way we could pick 4 elements out of the set if we cared what order they're in. What if we don't care about what order they're in?
Then you have to divide by where you have duplicates.
So now, we need to divide it by all the different ways that we can order 4 elements. How many different ways can I rewrite out this set in different orders once I pick 4 elements?
4 factorial.
4 factorial. You see that? So if I were to count this, I would have counted all 4 factorial of those sets, but I don't want to include all 4 factorial of each set. So it would have been, if we were now to count how many subsets can we do, it would have been 10 times 9 times 8 times 7 divided by 4 factorial. You with me? Now, we already have notation for 10 times 9 times 8 times 7. That's exactly what we mean by 10 sub 4. That's 10 times 9 times 8 times 7, right? So this is the exact same thing. Remember, 10 choose 4 is answering the question, how many 4-element subsets can I make of a 10-element set? By definition, that's what 10 sub 4 is. We're coming up now, finally, with our formula for doing this no matter what. So, that was 10 sub 4, or 10 times 9 times 8 times 7, over 4 factorial. Or 10 times 9 times 8 times 7 over 4 factorial. Here comes the tricky bit. I'm going to multiply it by 1. I'm going to multiply it top and bottom by 6 factorial. What's 10 times 9 times 8 times 7 times 6 factorial? 10 factorial. Because that's 10 times 9 times 8 times 7 times 6 times 9 times 4 times 3 times 2 times 1, which is 10 factorial. And notice that I can write 6 factorial. I can rewrite that as 10 minus 4. With me? And so, 10 minus 4 times 4 factorial in the denominator gives me the exact same thing.
Oh, yeah.
Okay, so here's the way that we're going to say it. N choose k, here's how we always calculate it. N factorial divided by n minus k factorial times k factorial. And that's how we'll compute it from here on out. Let's make this formula make sense once again. This time I have an n element set. With me? I need to choose a k element subset. How many options do I have for my first element? How many options do I have for what can go here? N. How many options do I have for what can go here? N minus 1. 1 less than n. Whatever n was, we're now at 1 less. N minus 1. What about here?
N minus 2.
N minus 2. How many options do I have for what goes last? N minus k, where k is how many choices I make. N minus k, where k is how many things were in the set. If there's one thing in the set, oh wait, n minus k plus 1, right? It's always going to be one number higher than m. How can I make this appeal to your intuition? Come back up here. Notice how many elements were in this list.
4.
So in this case, our k was 4. So we're going to have n minus k plus 1 options for our last element. What's our n? 10. Minus 4 is 6, plus 1 gets us 7. Think about it when k is only equal to 1. How many options did I have for what goes here if we just did a 1 element set?
1.
Then it would have been n options. Not n minus 1 options, n options. So it's not n minus k, it's n minus k plus 1. So if we had a 2 element set, then it wouldn't be n minus 2 for our last element, it would be n minus 2 plus 1. If we had a 3 element set, it wouldn't be n minus 3 for our last element, it would be n minus 3 plus 1, or n minus 2. So n minus k plus 1. where k is how many choices, how big the set is. Okay, does that make sense? Okay, so multiplying that out, n times n minus 1 times n minus 2 all the way to n minus k plus 1, you might remember that that's exactly going all the way back to our formula. When I said, what's our formula for n choose k? That's exactly what we said it was. That's n times n minus 1 times n minus 2 all the way down to n minus k plus 1. You always end one higher than whatever that is, or than whatever the difference between those is. So if I were to write something like 20 choose 5, what's the last number going to be?
16.
16. Let's check that. I'm going to multiply the first 5 numbers. 20 times 19 times 18 times 17 times 16. Yes, if I multiply the first 5, we end on 16. 20 minus 5 plus 1. N minus k plus 1 is always our last one. Make sense? Okay, so there's our formula for n choose k. But now, how many different ways can I arrange the k elements? If I have k objects, how many ways can I rearrange them? K factorial. So I need to count now, I need to divide by how many different ways I can arrange those elements so I'm not accidentally counting the exact same set in 2 different orders. So n sub k divided by k factorial. So here's one formula you could use if you want to think about it that way. Now this is just the exact same thing as this. Multiply top and bottom by n minus k factorial. And so that finishes the expansion there to give us n factorial, and then puts the n minus k factorial in the bottom. So that's where the formula comes from. You can remember this, or you can remember this. If you go look it up online, you're going to see this. You're not going to see this. But they're the same thing. Good? Okay, let's just do a very concrete case then. Let's say I say you have a 17 element set. And I want you to choose, how many objects do we say you're choosing from the set? 5. So 17, you're choosing 5. What's that going to be equal to? That's simply going to be equal to 17 factorial. Divided by, what's 17 minus 5? 12 factorial. Times 5 factorial. And this is a great way to leave it. Oh, sorry. Don't put time there. That's a great way to leave it. We don't need some big giant number, whatever it comes out to. Who cares? This tells me exactly how you counted it. So when you're answering these problems, when they blow up like this, I'm perfectly fine with you leaving it like this and not plugging into your calculator and writing that massive number. For smaller numbers, I mean, if we're getting in the realm of 6 factorial and smaller, you can quickly plug it in and see, or multiply it out and see. But for large numbers, it just comes out to whatever it comes out to. Okay, final example, final problem we're going to do. We are looking at a bird's eye view of some city. And so the grid is all the roads. We're looking at city blocks. So it's 10 by 10 city blocks, and this is our entire city. We're at point A. We're trying to get to point B. Our question is, how many paths can we take going from point A to point B if we don't allow backtracking? What do I mean by we don't allow backtracking? Let me show you the type of path we're not allowing. You can't go up, over, back, down, over, up, back. So green there would be an example of a dumb path, a bad path. No backtracking. You either always have to be moving to the right or moving up. So the question now is, how many different paths can we take through this city, getting from point A to point B? That's our problem. It's what I want you guys to kind of think about and try to come up with a solution for. How might we count that?
Can you cross other paths?
Yeah, we're just going to say, how many different ways could you go? You've got some GPS system. All these paths are equal length, whichever way you go. Notice that no matter what path you take, you're going to go over all 10 squares and you're going to go up all 10 squares. So there is no fastest path. All the paths are equal length. How many paths could you possibly take getting from point A to point B? So one option is you just go straight up and straight over. There's one. Another option is I could have gone straight up to right here, over, up, like that. I could have gone up to 2, over, up, like that. And every other path in between. I'm not going to mark them all out because there's a lot of them. The question is, how many paths could you take getting from point A to point B? How can we think about this problem? So think about each point in the path. So starting at point A, and we'll break this up to think about moving like in a video game where you have to move one tile each time. If I start right here, how many options do I have?
2.
I can either go up or right. Right? And then, once I make one of those options, whichever one I make, now I'm right here, how many options do I have?
2.
2. I can either go up or right. Maybe that time I chose go up, now I'm right there. How many choices do I have? 2, up or right. So, how many times do I make that choice in going from point A to point B?
The entire time.
19 times.
20 times. I'm going to have to eventually give you one example. I can go right 10 times and up 10 times for a total of 20. So I've got to make that choice 10 times. Or 20 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 times. And each time, how many choices do I have? 2. So I can either go up or to the right. Maybe that time I happen to choose up. For the second choice, how many options do I have? 2. And maybe that time I choose to go to the right. Times 2 times 2. And so the answer would just be, how many choices do I make?
2 to the 20.
2 to the 20.
Except for if you go all the way up or all the way to the right, you can't make.
Perfect. Because that's not really true. Once you use up all your ups, you can't go up again. So this would include counting the string up, 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 up. So that doesn't work. So what do we actually, how's one way we can think about this now in terms of subsets?
You have to, it's the ones that where you have 10 ups and 10 rights.
Yeah, I have to have 10 ups and 10 rights. So how might we choose that? What's a way that we could think about that? I basically take a 20 element string here, and I need to somehow choose 10 of them to be up, or choose 10 of them to be right. Because if I choose 10 of them to be up and make all the others right, that will for sure get me from point A to point B. I will for sure have gone up 10 times and to the right 10 times. So I got 20 element string here, and I need to just choose 20 of those, or choose 10 of those to be up, or choose 10 to be right, one or the other. It doesn't matter which way we go.
2 to the 10 plus 2 to the 10 more times.
Try and think about it in terms of what we just did. What the whole section was all about, the choose notation.
Oh, it's just 20 choose 10.
It's just 20 choose 10. That's exactly what it is. 20 choose 10. I think about I have 20 indexes here, and I need to choose 10 of them to be up. Another way that we can think about that is I have a 20 element list. 1, 2, 3, dot, 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 20. How many 10 element subsets can I make of this list? Give me one 10 element subset of this list. Give me one, anyone, doesn't matter.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
1, 2, 3, 4, 5, 6, 7, 18, 19, 20. Okay, some 10 element subset. If I were to go on this and put up wherever we have an index here, so up, 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 up. Sorry, gotta keep track of what I'm on. That was 4, right?
Uh-huh.
Up, up, up. And then we gotta skip to the last 3. Up, up, up. And then I go and I replace all the rest of these with R's. That will give me one of my paths. That would have given me the path. Let's see, how many times do I go up? I go up 7 times. And then I go to the right 10 times. And then I go up 3 times. It was that path. So every single path we can think about, start with a 20 element set, choose 10 indexes, And whatever those 10 indexes are, make those your ups, and the rest are going to be rights. And that's all the paths you could possibly take. That make sense? Okay, so that's one of the ways that this is really useful. So now counting that, you can really quick just calculate that. What is that? 20 factorial over 10 factorial over 10 factorial. Plug that into the calculator real quick. Impress your friends. And you say, oh yeah, it's just this big number. Okay, any other questions? Okay, then let's end it there and delve into some of your homework.